I would like to introduce our next speaker, Andreas Enotiadis, who will be presenting the new Encrypted Protocol Stack and how to deal with it. Andreas is a CTO 5G at Cisco and is coming to us today from Greece. This is Andreas' first time presenting at Nanog, and it's a pleasure to have him speaking with us today. Welcome to the stage, Andreas.
I'm assuming it's the big green button, right? Thank you, Michael. Thank you, John, for bringing such a great audience. I wouldn't have done it by myself. John and I are old colleagues and friends for 20-something years. Yeah, for a long time. I'm not sure whether you guys can handle two British accents back-to-back on the graveyard shift, but at least mine's fake. Oh, it's acquired anyway. So I'm here to talk to you about the emergence of QUIC. Encrypted Protocol Stack is short for QUIC, and its friends in the protocol stack, and how it's actually appearing on the internet. This is work that we're doing together with my friend and colleague Bart van der Velde, who couldn't be here today. We had to split. He had to go to Germany for something else. I stuck on the West Coast to also do this presentation. And it'd be remiss of us, abracadabra, yes, not to remember that this was started by our friends and colleague Dr. Mark Gallagher, who unfortunately passed away a few years ago, and we're continuing his brilliant work in analyzing these things. So what we're going to do today is we're going to talk about, we're calling it very boldly, the new internet, because there is a massive shift in the way traffic is actually going through the internet, and it has impacts on places that we'd never even think about. So we're going to talk about a little bit on how traffic is evolving by looking at different places and different snapshots in time within the global internet, and the impacts that this kind of traffic is having on our networks. And then we're going to look at what we've been working on as a toolbox to actually mitigate the impact of this traffic or manage the impact of this traffic, and some use cases that this toolbox enable, because a lot of the ways that we're actually dealing with traffic today in the internet are being upended by this evolution that is being driven primarily by the great hyperscalers, Google, Meta, and primarily the other video players. So let's start with the traffic. Back in oops, sorry, I went too far. Back in 2020, we landed ourselves an enormous batch of EDRs from a very large US carrier. It was 6 months worth of EDRs that they dumped on us, and they said, "Oh, guys, we're seeing strange things happening on our mobile network." It was a mobile network. "Can you tell us what's going on?" So we faithfully spent significant amount of time, crunching through that data and analyzing them. And there were certain conclusions. Some of them are pretty obvious. Some of them less so. So the first one was 90% of the volume was encrypted in some form or another. No surprise. I mean, you guys know that, if it's not HTTPS, it's not flying around anymore. But there were lots of different kinds of encryption emerging, and that's something that we'll see a little bit later. The other one was 70% of the volume was actually going to 10 different, or coming from, rather, 10 different destinations. And in fact, if you did a little bit more analysis on this, you would actually, and delve a little deeper, you'd find there's 12 destinations, actually 80% of the volume, and that was already in 2020. So quite early, which starts generating the concept of an elephant destination or an elephant source, depending on how you look at it, which side of the house, rather than elephant flows in our environments, and starts implying that it might not be one network anymore. It might be a few separate networks all riding over the same underlying infrastructure. The third piece that was interesting is that 50% of all interactions, flows, so interactions as you call them, were actually DNS, which is really interesting because it actually pointed to the fact, and there was a really nice presentation earlier by, I think, our friends in Kentic about CDNs, how DNS is being used to a very large extent as the content load balancer in many ways, shapes and forms, and that kind of indicates the same thing. But the one thing that kind of had us scratching our heads is, oh my God, what is this QUIC thing that's showing up as 20% of the total traffic? I mean, the networks are supposed to be TCP IP, right? What's this QUIC stuff? And it didn't stop there. If we look, and I'm going to go back to detailed analysis, we've been snapshotting using some more, no longer analyzing enormous lists of EDRs, but actually snapshotting in real time networks around the world once we saw this thing. And we've seen that the percentage of QUIC traffic has been growing at a fairly rapid rate annually, and it's now averaging 45% globally, with Latin America being a little bit higher on the lists, actually going over 50%, and North America being a little bit lower. I suspect the North American number is actually lower than the Latin American number because there is a significant amount of fixed wireless access being calculated within those numbers, because all these snapshots are coming from mobile service providers. It just happens to be helpful for us to actually measure mobile networks, and in North America, mobile providers do provide a fair amount of fixed wireless access, which we have seen that has a lower amount of QUIC traffic on a qualitative basis. But the overall important thing is QUIC is now closing on 50% of the global traffic. It's no longer a TCP IP network, because I'm not going to teach my grandmother to suck eggs, but you guys know about QUIC, right? QUIC is primarily a UDP-based protocol with TLS 1.3 as the encryption layer, and all the flow control, so everything about how it behaves on the network, moved up to the application. So it's a completely different animal than TCP. It's not a bidirectional session-based environment. It's much more suited to RPC type communications. You know all these things, but its behavior as a result is entirely different to TCP. So it's worth delving a little bit deeper, and we've started doing that. So, going back to some of the data that we saw in aggregate form and looking at them in a little bit deeper base, we can see that QUIC is 40-something% of the traffic, 40% in this particular case. But the interesting thing is that what we're calling the big five volume producers, so YouTube, YouTube, Meta / Facebook, Netflix, and who else is it on this list? But yeah, actually, Amazon is on that list and whatnot. They are 50% of the total traffic. And they, as we're going to see later, are primarily focused on moving QUIC traffic more and more as it happens, okay, from a volume perspective. From an interaction perspective, it's completely different. You can see that TCP has now, and the rest of the world, the multiple hundreds and thousands of destinations on the internet, actually are moving a lot more traffic around, or a lot more interactions, I'm sorry, but the volume of traffic is not as big. And that's also fairly logical, because most of the traffic that's being moved by the big five, as I was mentioning earlier, is actually video traffic, which is high volume, and has been one of the very first applications of QUIC as a protocol, because it's very fast session establishment, because it's very amenable to its own flow control, and because it's encrypted, and because it can be controlled very, very nicely and whatnot. There's a ton of reasons why. Another one, of course, is that a lot of people in this space are using the open source ABR video player, And switching to a QUIC protocol on that is simply a matter of one compiler switch. So it's also convenient and not just easy. The same pattern persists worldwide into 2023. We did a number of measurements around LATAM, North America, and in Europe around around May this year. I think that's about a month ago, or a little bit less than a month ago. And we're seeing pretty much the numbers stabilizing where we thought LATAM having the higher number. LATAM is interesting because it's very much a mobile device first market, and you will see most of the QUIC traffic being generated by the actual apps on your mobile phone, and the apps are the ones that are owning the complete food chain. EU is used fairly similar. As the US is lower because it contains a fair amount of fixed wireless access traffic, so it's less mobile devices from a percentage basis and more other kind of devices like PCs, like TVs. And also worth noting that the only holdout from the big traffic generators in the markets from QUIC is Netflix, because I don't know why, and I do know that they actually are using the same video player, so they could switch anytime that they wanted. But Netflix has a very, very optimized TCP stack that they're using for very fast start. You've noticed how interactive Netflix is as a platform, so they're probably loath to use it. I'd like to, if there's somebody from Netflix and can educate me, I'd love to know, by the way. So this pattern is becoming global, and I suspect it's going to keep growing as more and more platforms start switching into the QUIC domain. And the problem is that it's not an innocuous event. It doesn't just say, oh, well, it's all right. I was moving IP packets, I'm still moving IP packets. What do I care? It actually challenges a lot of what we're actually been doing, or we have been doing in this industry for the last 30 odd years. And the first assumption on which we design systems, we build networks, we even talk about our networks, is that most of the traffic is TCP IP. The emphasis on TCP. The general assumption is 80% plus TCP, and it's not that anymore. And the behavior is very, very different. Okay? TCP has a certain response way, right? You drop a packet, then close the window, somebody will back off, stability will be restored. And this assumption is implicitly built into our networks. Think about a radio access network in mobility. I mean, I come from mobility, so these examples come to me a little bit more naturally, right? That base station doesn't know anything about layer 3, layer 4, layer X. It just sees PDUs and it has a schedulers and it services TTIs. It drops a PDU because its scheduler has overflowed. It assumes the higher level protocols are actually going to take care of it because it is TCP IP. Well, it isn't anymore, not fully, not 100%. So the kind of network cooperative fairness of TCP is now being challenged. Look at that. Look at the other side of the chart, right? This is some of the really great work that Jeff Houston and his team have done over APNIC, where they've actually measured explicitly how these networks, these protocols behave in a network. So you start with a QUIC and a TCP flow on a network. A QUIC flow will take by default more because it has a more aggressive implementation of its congestion management algorithm. Now, it's not a different congestion management algorithm, right? QUIC still uses BRR, Reno, QUIC, the standard congestion management algorithms, but now they're being managed by the application rather than anybody else. The fun starts when you start adding flows. So you add 2 TCP flows, and instead of this, doing a rebalancing and everybody taking their fair share of the network, QUIC if anything, increases its share and pushes the TCP flows on the side. And the more you put on, the more evident it becomes that QUIC flows are actually focused on one thing, my app. Uber, who by the way did switch to QUIC for its app a few years ago, did a really nice test in, I believe it was in India, if I'm not wrong, where they actually measured the behavior of their application under TCP and QUIC. They had two versions of it in different kinds of networks. They found that the improvement in quality of experience was bigger the worse the network is. So if I'm on GPRS, anybody remember GPRS? Then the improvement that I see by switching to QUIC is actually enormous, which means that QUIC is going to be driven from the user experience. The users are getting a better quality of experience, and they will be overwhelmingly using the QUIC-based version of the application and demanding it. So we can't just say, because I've seen that, especially as an enterprise policy, say, oh yeah, that's no problem, I'll just block UDP 443 at my firewall, and suddenly all will be well again. No, the users are never going to allow that, because the quality of experience that they're getting. So the network design assumptions that we have are being challenged a lot. Our traffic management assumptions and our traffic management behavior is being challenged by QUIC. And that is really, really evident because some measurements that we did in a Northern European provider back in about a year and a bit ago show that really on the top 5 apps as they're being moved to the network, QUIC is the dominant protocol already. And these are the biggest and the fastest growing protocol stacks around the world and the fastest growing applications. So that's one thing that we need to keep in mind. There's another thing, though, that we need to keep in mind, and that QUIC is not coming alone. Typically, it's part of a complete stack evolution that, of course, is the shift to HTTP 3, which in itself is not a problem, but typically is accompanied with DOH, so the transition of DNS from a classical hierarchy that can be intercepted, can actually be manipulated, can be used for CDN type of deployments, to something that is controlled to a very large extent, again, by the application, because the application now opens a DNS over HTTPX request to its preferred DNS environment. Example in case, if you install Firefox in North America, its default configuration behavior is DOH directly to Cloudflare. Bypasses, and I mean on your PC, I'm not talking about a mobile device. Bypasses everything, goes straight to Cloudflare on DOH, completely uninterceptable. So that's one thing that starts to disappear, which was a very useful piece of information that we could use for doing things in the network. But we could still catch a fair amount of information because we had eSNI, right? Server name indicator. Typically, we have a virtual server sitting behind a physical environment, and the server name indicator is in the clear. In the request, I can say, okay, at least they're requesting something. Well, no, because actually eSNI came along, RFC 80744, and that one encrypts the SNI request, and that's gone already. But that's all right, ALPN is still in the clear, isn't it? Actually, no, because there is a current draft on the IETF, the draft eSNI is down version 16, I believe, which encrypts everything all the way up to and including the client hello. So all the tooling that has been used to essentially do deep packet inspection of every form, intercepting information, understanding what traffic is in order to apply some kind of policy, routing, cache determination and all that is rapidly going away. And it's becoming quite ineffective. And that was kind of the reason why the original request, can you have a look at our traffic, came in back in 2020. This is not new. It started happening quite some time ago. We're just seeing its volume grown to a very large extent. And therefore, anything that depends on package inspection needs a different approach because, if we look at another snapshot from another European provider on a per application basis, that's, it's an American operator. As on an overall volume, QUIC was 40%. But if I look at things like Facebook, or Meta actually, all of the Meta applications, Instagram and what on, QUIC was nearly 90%, so 80-something percent. And if I look at YouTube, who's the originator of QUIC, right? It's already at 90% and climbing. So when you're trying to do policy to all these major applications, that's something very common, particularly in the mobile space and particularly in North America, as you probably know. What policy and whether it's nice is a different question, but there is policy being done on these flows, becomes completely untenable. So this packet inspection technology that will allow you to do something with this traffic needs a completely different direction. It's never going to be the same. Eventually, we will never have this kind of information that we always had when everything was nice and in the clear and we can make decisions. But we're going to have something, or we've got to have something in order to get to that space. And this stack, all these pieces are in business. Everything is standardized. The last thing is missing is ECH, I believe, and it's to get a full RFC, but it's already a draft on the IETF. But everybody is implementing it, and as far as I know, it's moving from a primarily video delivery toolkit to a much wider environment, because apart from its very malleable control from the application, apart from its encryption, it also has some really, really cool other aspects. It's zero RTT. There's no man-in-the-middle capability because TLS 123 end-to-end encrypted. So it's actually a cool protocol in every way, shape, and form, and the users are actually getting a benefit. Microsoft is starting to support it, as far as I can tell, for their Azure-based applications, which is much more enterprise-oriented environment. So blocking QUIC is never going to be the answer. That's what I'm trying to say. We need to find other ways. Okay, have I sufficiently scared you? I hope so. So we've been scratching our heads around what we can do in this space, and we've come up in partnership with and close collaboration actually with a startup here in Seattle called Opanga Networks, who are just down the road. Hats off to them because they've done some really, really cool work in this space. And we've come up with jointly with a toolbox and set of use cases that we're starting to play with in this space, and which you guys might find quite useful. Going back again a little bit, there was a very interesting question coming in from a certain service provider, as an example, which said, I've got Snapchat screaming at me because the filters are not downloading fast enough into the user's device. I had to go ask my son what the hell Snapchat filters are, because I had no clue, okay? I admit, it's those moustaches and glasses and stuff that actually you can put on top of videos. But the point is that those are file transfers, as opposed to the other part of the Snapchat traffic, which is actually short-form video. And if you can't distinguish between the two, and for some reason, which is not uncommon in North America, you're doing certain kind of policy on video, and you're doing it based on a source destination, and suddenly source destination, the only thing you have is Snapchat or the Snapchat CDN, you start doing policy on the video and the filter. And the filter, which is a download, doesn't download fast enough to appear in the place as a moustache, and the kids get pissed off. So that is an important problem, because there is a complaint from the customer base to the service provider. There was another one which said, wait a minute, if you can't actually, some users were doing YouTube video premium video downloads as a means of measuring the throughput of a network. And when the service provider lost the capability to actually distinguish between a video stream and a video download and started applying the same the throttling bitrate policy onto those YouTube those downloads, suddenly they were being unjustly and unfairly, but hey, what can you do, called a non-performant network because they were rate limiting downloads unintendedly, because they couldn't determine. So these were the kind of questions that started coming to us and kind of drove us to work on figuring out what it is. And if we step back for a moment and think about basic principles, there is some information that will never go away because we have to route the packets. And because between the packets there's an interval, and that interval is measurable, and because the payload size is always going to be there. So we know where it's coming from and where it's going, source and destination IP address, we know the payload size, and we know the packet interval. So is it possible to build some kind of information just on this data, because it's the stuff that will never go away? That was kind of the challenge we set ourselves to work on. Well, it turns out that application, and especially video, which is the bulk of the traffic, as we saw earlier, varies very much by protocol and use case. So long-form video over TCP looks different than short-form video over TCP. It looks very different than long-form or short-form video over QUIC, because QUIC has a much faster off-the-blocks behavior and therefore doesn't need to actually buffer as much on its first start. Looks completely different than a live stream. Looks completely different than download. All these are time domain behaviors. They don't look at anything else. So they're available to us because source destination plus payload size plus interval will always give me this information. The trick is, can I actually figure out fast enough what kind of flow it is? That's a useful little piece of information, because now I know which CDN, I know which kind of flow. That gives me a fair amount of information that I can use for it. So the first piece of the toolkit is time domain flow recognition, which is being able to observe all flows, profile them in the time domain, and figure out what they are in real time, as in sub-milliseconds, so that you can actually make decisions then on how to carry it. That's the first part of the toolkit that we put together. And what we can actually profile in reasonably good, well, actually really good accuracy, as opposed to 80 or 70% or whatever, 90 high. Accuracy is between different forms of content, of streaming content, so short form, mid form, long form. Short form is something like Snapchat, mid form is something like YouTube, and long form is something like all the major streamers like Netflix, Prime, HBO, etc., 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 in general. So we've got different types of streaming content. We've got real-time communication, one-way or two-way, live stream or back and forth like a video conference. And we have downloads, and we have really short-lived flows that really you don't care as much about, because they come and they go. They're very short interactions that happen in the network. The second thing that comes to mind, and we as networkers tend to think in a certain way, which is, okay, whatever I do, I have to do to every packet that goes through my network, because I have to have total and absolute control. And that comes from the fact that we're actually writing them one by one, right? So we know everything that happens, or we should know everything that happens to every packet. But the interesting thing is that we may want to know, but we don't necessarily want to act on a network unless there is something, to the point of John's earlier presentation, there is something happening which warrants acting on the network. So an interesting thing is, if I don't have access at the level of the counters of the network because I am dependent on downstream providers that are doing things. So for example, there is congestion happening at a very much of an access network. How can I actually figure out there's something wrong in my network? How can I infer that there is congestion? So second part of the toolkit is how we can actually infer congestion by the behavior of a flow in a time domain and make a decision on taking action based on this inference. And the third piece of the toolkit that you need is programmable traffic management, of course, which is something that we already have, which is, okay, once I've figured out, okay, it's this kind of flow, oh, there are conditions in the network that require me to take action, okay, I can then look up my policy and say, okay, this is what I'm going to do to this traffic on a per flow basis now, rather than on a per packet basis, because it's the flow that is important in this when we actually put it in this context. So the way we've put the toolbox together, and it's very much a toolbox at this stage, I mean, there is no actual product or anything that I'm talking about, is the tooling that we are working with, is the basis that we're building different use cases for it. So observation of flows, inferring what they are, inferring whether there's congestion, and then applying policy. And those three are independent functions that can be distributed along the network in different ways. So use cases that we've started putting together is, first of all, monitoring and analytics. You know, all those lovely pictures that I showed you, except for the first one, which was the analysis of the EDRs, actually are coming from this tooling. Well, they're coming from the Kibana interface on top of the Elasticsearch that actually is receiving all the telemetry that is generated from this tooling. But the ability to analyze this traffic in depth and in multiple different ways, and knowing in real time or in near real time what is happening to your network is a perfectly valid use case per se. By the way, the bottom snapshot I didn't show, but actually this is a snapshot from a fixed network in Europe that we did using EDRs again in this particular case, some time ago, but it did show that QUIC was 41% as well. So it does happen in fixed networks, albeit not necessarily the same source destination environments. But the point is that the first thing and useful thing is to find out what's going on, because that tells you what you're going to do further. The second one is the general use case of custom policy enforcement. I can now differentiate using this tooling that it's a Snapchat video versus a Snapchat filter, so I can only apply the policy to the video. I don't apply the policy to the filter, whatever policy that is, which means that the moustache gets in place in time rather than out of time and looks completely strange, and then the kids are happy. So that's the general thing of whatever policy you're doing. There are specific and interesting sub-use cases of this policy that I'm going to touch on that we've built as use cases though. The first one being time domain shaping. One of the interesting things that we saw is that all these are really predicated on video. It's video, 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 and video. And it's logical because the video volume is enormous on the network, and it's the one that's making the impact and the difference. Well, video players behave in a very, very specific manner. Okay? They buffer, as you probably know, a significant amount on the user device, and that's because they don't want to be dependent as much on network, on a dynamic network experience. It makes perfect sense. Now, that means that video flows are very amenable to time domain shaping, which translates to, if I am congested for some reason, congestion inference, and I have detected that this is a video flow, second part of the toolkit, I can say, okay, can you buffer a couple of hundred milliseconds this flow so that I can let everybody else go through, because QUIC was pushing everybody out of the way and the TCP flow was starving and they were dropping packets like crazy until things stabilize, and then I can release the flow again in a certain way. And this is cool because it actually does all that without impacting user experience. The user doesn't know anything. I mean, you can't read it, but this is showing this situation in a Formula One race, real-time cast. And the user experience was exactly the same because it was allowed to use the buffer for the right amount of time. Same thing, but in a completely, same technique, but in a completely different environment. Shared access networks, becoming more and more common thing around the world. And typically the way shared access networks work is, or interconnects actually, but this example is from shared access networks. The application is fairly similar. You get a pipe with a committed information rate, and that's kind of your the amount of money that you pay to receive traffic and send traffic to the access network. And then if you burst over it, because your physical pipe is bigger, you pay, depending on the contracts, anywhere between an arm and a leg, a pound of flesh, or some other things. So you really want to stick within your CIR, but the problem with sticking with your CIR is you put a policer on the link, and once it starts going over the CIR, you start dropping packets, and the user experience starts getting damaged, and everybody starts getting annoyed. But if you actually can detect that I've got a whole bunch of video flows going through that link, and there is congestion because the policer went into action, but I can actually do time domain shaping of those video flows because they are bufferable, and I can actually alternate between them so that I don't even have to do it to one of them. I can stick within my CIR without impacting quality of experience. This is a real example of a use case that we did in Australia that we experimented with, which was very, very successful in maintaining the interconnect costs of the particular ISP to something very, very useful. And the final use case, which we're kind of playing with because post-COVID it has become a very important thing, is there is now an expectation that when I go on a video call, it works everywhere. And when it comes to mobile networks, that's not necessarily something very, very reliable, because congestion and flipping between bands on a mobile network and falling into congested bands, even in 5G, can be very, very useful. So it's a nice use case which says, well, wait a minute, but I can see, even if it's QUIC, if it's completely encrypted, if I can't see anything about it, just from its time domain behavior, I can see that this is a video conference because it's a two-way stream. It has a different time signature. So if I'm offering this service, or if I want to do this policy, I can say, okay, I can very easily measure the bandwidth usage of that particular stream. I can subtract it from the link bandwidth, and I will shape or apply policy to the rest of the bandwidth, protecting that link. Again, it relies on the capability to recognize flows in the time domain in real time and do things to them. So, as a conclusion, our traffic is getting encrypted, and it's getting encrypted in ways that we can't intervene in anymore, because TLS 1.3 does not allow any kind of man-in-the-middle type of encryption. So QUIC flows with eSNI, ECH, and all the goodies are now encrypted end-to-end from application to server. And we have progressively diminishing capability of actually understanding what the traffic flows in our networks are. And they're here to stay because everybody's adopting them, and they improve the user experience. And the user experience is the #1 driver in the industry, as we know. So what we think, and we're putting on the table for discussion, is that we need to start looking at an IP flow-centric approach that actually can scale, as opposed to trying to handle every single flow, handling only the flows that matter, only when it matters, as an approach to dealing with this evolution looking forward in traffic management. Thank you very much. And questions, tomatoes, yogurts, all acceptable.
Hi, Steve Wallace from Internet 2. I have a question. Do you see data-intensive scientists who need to move large data sets around using QUIC or experimenting with QUIC?
Sorry, I'm a little bit deaf, so I need you to repeat the question, honestly.
So scientists that have large data sets,
Oh,
do you see them using QUIC?
I wouldn't know, in all honesty. I really wouldn't know. We haven't. Most of the measurements that we've done
Mobile.
have been in consumer-oriented networks. Now, interestingly, this is something I want to start doing more and more. What I showed was snapshots rather than a systematic measurement model. I would like to transition this to a more systematic measurement model. What I'm trying to do is put together essentially a small NOC-based appliance that you can actually plug in a span port on your network, turn it on, completely passive, leave it there, and it will keep measuring and start giving everybody information to what this is going to be. But no, I wouldn't know the answer to that, I'm afraid.
Andrew Dahl, question for you would be, I consider QUIC kind of a selfish protocol because it doesn't really think about others as much as perhaps others would in terms because it doesn't provide out-of-band signaling that you would normally see with TCP. What have the developers of the protocol thought of in terms of making it less selfish for other flows that exist that it doesn't necessarily know about?
It'd be great, but the point is that what's their incentive?
Well, they live in an ecosystem with other people, so the incentive is also to keep their flows going as well.
We can go into business and human dynamics, but you're absolutely right. I mean, one of the reasons TCP is great is that it's actually something that we all have a shared way of how we deal with it. And now the problem is, do the application developers start caring? What's going to happen? Another way of asking your question is, what happens when QUIC becomes 90% of the traffic, right? They're going to have to figure out a way either to live with each other or to cooperate, or we'll end up with, 10, 12 internets battling for our attention over a common infrastructure. We as service providers are going to have a fairly hard time figuring it out unless we can start finding ways, and that was kind of our attempt to start managing QUIC traffic as well in certain ways. But I don't know the answer. I really don't know the answer to that because it gets out of the technology space and into the business policy human space that's, I don't know. Oh, sorry.
Hi, Matt Petach sent a question. Do you have data on how QUIC behaves when there is only QUIC, no TCP? Will they establish fairness between them, or are they still selfish flows?
So when there's no congestion, that's fine. I'm assuming you're asking when there's only QUIC and there is congestion, right? So I haven't seen any measurements on this yet, and it's actually not going to be QUIC, if we're going to be exact. It's going to be whichever application is actually using QUIC, because the flow control is not in the protocol itself, right? It's in the application. So I believe that Jeff Houston plans to do some measurements similar to the ones that we were talking about on this. So he's the master of this game. As soon as he comes up with something, I'm sure it will be published around, but I have no clue how it would behave. I suspect what's going to happen is whoever has the most aggressive algorithm is going to win short term. I mean, for example, I've seen YouTube in certain cases encounter congestion, and when they see congestion and they see packets drop from the stream, what they do is they open multiple connections and start blasting the traffic and saying the application will deal with out-of-order packets and everything else. I just want to get all the packets through. So if that happens for multiple applications, it's going to cause thrashing, right?
Thanks.
Not that I've seen it, but that's my conjecture.
Linda Dunbar, I have a question. How do you identify the flows? Because you talk about the first thing is to identify the flows.
So the flow identification at its lowest level, okay? So you want the underlying technology or the data sets that we use? The data that we use is the temporal behavior and whatever information is visible in address. At a minimum is going to be the source and destination IP address, which is the CDN. If there's more, we will use, and it's not encrypted, we will use more. The way we do it is we actually have a bunch of vectorized models of different kinds of flows, which we download directly to the detector, and there's an inference engine that actually determines what type of flow it is within less than a millisecond of the flow start.
Because lots of applications use anycast address. So you'll see the same address, which can be many different flows, right? There's address translation. So
Oh no, QUIC! See, you can actually see that because there's one piece of information that's in the clear with QUIC, and that's the connection ID. So each QUIC flow has at least one connection ID, and if there's multiple QUIC flows, they even have a related connection ID. So there is a way to correlate and extract this kind of information. I can tell it's so. It's a really good question. I asked myself the same thing when we first looked at it. If you've got a CDN that's dumping a ton of QUIC towards the same network that's sitting behind a NAT, and therefore it's a single address, how do I distinguish it? There's a connection ID in the clear, which allows you to do that.
thank you. Thank you.
So I guess, am I the last thing that stands between the gentleman and beer? No, there's more. So let us get you to beer as soon as possible. Thank you, Michael.
Thank you.